Okay, that was all for sets. For the time being, we are going to come back to sets when we talk about functions and cardinality again. But at this point, we are ready to define the concept of a relation. And simply, a relation is a subset of the Cartesian product of A and B. Simple as that. We call this a binary relation from set A to set B. For instance, if set A is consisting of elements A and B, and set B consists of 1 and 2, and these are example relations because you see A times B can be written as A1, A2, B1, and B2. This is the Cartesian product of A and B. Any subset of this, and there are 16 of them, any subset of this is a relation, a binary relation from set A to set B. Here we, of course, include everything, and we also include the empty set, and we also have these others as example relations. Okay, simply put, a binary relation is a subset of the Cartesian product. Now, if the two sets A and B are the same set, we say the relation is, well, instead of from A to A, we just say on A. Okay, relation on set A. Um, and if an ordered pair AB is an element of a relation R, well, of course, this is a standard notation, but we also have this shorthand notation. We just put the relation R in between the two elements. And this notation shouldn't really be weird to you because, well, this, for instance, is a relation representation. Here, the ordered pair and the set R are related through the relation is an element of, okay? Or for instance, this is a relation. The integers, let's say, 3 and 5 are related through the relationship of less than. Or for instance, um, uh, let's say two sets, A and B. When we say A and B are equal, A and B are related to each other via equality relation. These are all relations. A subset is a relation. As we have stated, these are set relations. Or we have other relations among numbers, among other structures. For instance, we have isomorphisms in graphs. That is also a relation. So any such structure you can think of, we can build a relation. And this is the notation we use. Two elements separated by the symbol of the relation. It could be something like R, or it could be a special symbol. Okay? And of course here, if they are not related, the elements A and B are not related through the relation R, we just use this notation. And we also have the concept of the inverse relation, and this is the notation we are going to use. I'm sorry, I forgot to change this because this was the earlier notation I used, but usually we are going to use this notation. Sometimes you can see the overbar, but it coincides with our notation of complement, so I'll try not to use it. So the inverse relation simply is the relation from B to A when you switch the orders of the ordered pairs. Simple as that. So if a relation R is from A to B, its inverse relation, this, is from B to A, and all the ordered pairs are just switched. That's it. Now, how do we represent relations? Well, first of all, uh, observe that a relation is itself a set. So you can always use the list method like this. But as I said, sometimes this is a little bit tedious. You have to just list out all elements. It can get long. And also, this method is not really useful when identifying certain properties of relations. So for this purpose, we use two more representations. One of them is the digraph representation, or the directed graph representation. We are going to talk about directed graphs when we talk about graphs in general, but for the time being, you just have a set of vertices and a set of edges with directions between them. So the direction indicates the order of the ordered pair. For instance, if you have the pair 0a, then you have an arrow, which we call an edge, from element 0 to element A, and these representation of elements we call vertices. Okay, each of these are a vertex, and in between we have these arrows which we name edges. Okay, of course, since the order of the ordered pair is important, the direction of the edges are going to be important. Here we see a relation R1 from set A to set B. So here on the left-hand side, we have the elements of A. On the right-hand side, we have the elements of B. And on the right, we see R2, a relation on A. Okay, B is not involved here. So instead of just writing 0, 1, 2 here, 0, 1, 2 again here, you don't need this. You can just use each element once. And if you have a relation between the element and itself, like this here, 1, 1, you just put a loop here. Okay, so we have 0, 1 this here, we have 1, 1 this loop, and 2, 0 this here, and 2, 2 this loop here. So this is the D-graph representation, and this, when you look at it, this tells us some properties that a relation has in a graphical manner. So this is the reason we prefer this over the list method. And we also have the 0, 1 matrix representation. Here we have a matrix, and each of the rows indicate one element of the first set, A here, and each of the columns represent an element from set B. Okay, now the enumeration here is not that important as long as you keep it consistent throughout your statements and definitions and derivations. It doesn't matter which order you choose, but of course you need to keep it constant. Okay, so for instance, I chose the order 0, 1, 2 here and AB here. I could have chosen like 2, 0, 1 here and BA here. It doesn't really matter, but of course, throughout my derivation, throughout my statements, I need to use the same enumeration in all of my matrices. So how do I fill this in? This is a 0, 1 matrix, so the elements are going to be either zeros or ones. And whenever I have a relation between two elements, I put a 1 in that location. So I have 0A, so 0A, this element here is 1. I have 0B, so 0 here, 1 here, this element is 1. I have 1A, 1A, this element is 1. I do not have 1B, so 1 here, B here, this is 0. Again, I do not have 2A, so 2A, this is 0. And this is 1, corresponding to 2B, and so on. You see, this is a 3 by 2 matrix because the cardinality of set A is 3 and the cardinality of set B is 2. So this is a general rule. If set A has m elements, set B has n elements, the 0, 1 matrix will be of the size m by n. Okay, and here, remember R2 is a relation on set A. Therefore, the number of rows and the number of columns have the same number. And this is a 3 by 3, a square matrix. Since it's a relation on a set, it has to be a square matrix because each element should be represented both in the rows and both in the columns. And how you fill this in is exactly the same. Of course, you need to be careful about the loops. The loops, of course, represent the elements on the main diagonal. So I don't have a loop here, so this is 0. I have a loop here, so this is 1, and this is, there is a loop here, therefore I have a 1 here. And the rest you can fill with by just looking at either the list or the directed graph associated. Of course, if you have the directed graph, you can obtain the zero on matrix and vice versa.